Hello everyone, I'm MT Tawhiduzzaman, a PhD student at the Department of Computer Science of Virginia Commonwealth University, VCU. I'm about to present our research work titled WiPT, Wireless Sensing-Based Low-Cost Physical Rehabilitation Tracking. Besides of myself, this paper is authored by Stephen M. Hernandez, Dr. Peter E. Pitcoy, and Dr. Ifan Bulut. All of us are from the Department of Computer Science, except Dr. Pitcoy, who is from the Department of Physical Therapy of the same university, VCU. In this paper, we have used Wi-Fi sensing as the wireless sensing technology. I'm about to discuss Wi-Fi sensing in brief first, then I shall go through the architecture of our proposed system WiPT and the evaluated results of it. Let's start from the basic. What is Wi-Fi sensing? Wi-Fi sensing is a Wi-Fi signal analysis methodology that can be used to sense different environmental and physical attributes and actions. It is a device-free system, which in contrast of camera and many other sensor-based systems can work without any light source and does not require any line of sight. That is, it can be performed even with solid walls in between the sensors and the targets. In the right side animation, we can see how the received signal fluctuates depending upon a hand movement within the plain Wi-Fi transmission line in between a Wi-Fi router and a user device. We can analyze these sorts of properties using two types of data from Wi-Fi capable devices. One is scalar received signal strength indicator, or RSSI, and the another is a complex vector format named channel state information, or CSI. In this study, we have used CSI data using our own developed toolkit available as an open source project in GitHub. We compute the amplitude and phase of the received CSI frames over the 64 subcarriers of our used ESP32 devices. These ESP32 devices are the core hardware needed for our proposed system, WiPT. We use one of these devices as the receiver, or RX, and pair another of the same device with it as the transmitter, or PX. Then any movement within their multipath transmission line is captured by the CSI data in the 64 subcarriers of these devices. But why have we used ESP32 instead of the other market-ready devices? As our work's title claims, our solution is low cost, and each ESP32 device costs below $10 in the current market. Additionally, these are lighter and even more computation capable than the other available devices in the market, like Intel 5300 NIC, Atheros, or Nexmon, as shown in this table. These are why we use the ESP32 devices for our study. So after collecting the CSI data using ESP32 device, as well as our developed CSI toolkit, we need to process these data before providing these as inputs to our machine learning model. Firstly, we take the moving average of the amplitude of each subcarrier using a specific window size, which signifies the duration of investigated action. Then we run principal component analysis, or PCA, for dimensionality reduction, as well as to reduce noisy data. After these steps, our CSI data get ready to be fed into our DNN model, which targets to reduce the loss function with continuous predictions of the actions classes. By extensive optimization of our model, we have found that 4 hidden layers work better for our equipment-based exercises, while 2 hidden layers are good enough for the other datasets. It is noteworthy that we have used a drop-off layer after each hidden layer to overcome the overfitting problem in our model. To evaluate our proposed system, we have experimented with 4 sets of physical therapy scenarios. One is for physical therapy on wrists and fingers. We have classified 3 actions by 1 volunteer in each group with 1 single pair of transmitter-receiver. Movements of 2 hands and 2 legs were jointly studied with jumping jack action for a whole body movement classification. Lastly, we have studied 4 equipment-based exercises using 3 pairs of TXRX and 5 volunteers. We can see the studied wrist movements in the right side GIFs here. As I said, we used 1 pair of TXRX for this study. However, the pair is placed vertically, that is at the top and bottom of the hand at a distance of 50 centimeters apart. So the signals get a thinner view of the palm from this angle, and to our understanding, it causes pitch and yaw movements to be less recognizable. For example, 72.6% is the accuracy for the pitch action identification here. But the rolling actions provide the signals a broader view of the palm to make recognizing this motion more accurately. Overall, we have achieved 85.1% accuracy in classifying these three actions. Classification of the three finger movements as shown in the GIFs on the bottom right side is found to be even more successful. The accuracy in this case is 97.13%. Here, we stationed the TXRX pair horizontally along the palm at a distance of 60 centimeters. For a whole body movement experiment, we considered 5 actions like raising up, down the left arm, left leg, and right leg, along with the jumping jack action. We used one TXRX pair horizontally along the eye level. The pair had a 2.4 meter distance in between and from front to back of the volunteer in this study. For leg and jumping jack movements, the accuracies were pretty convincing, but the arm movements were found to be confusing with the counter side's leg movement. This can be explained from 3 angles. 1, the arms are tinier than legs. 2, while raised, the arms tend to go at the edge of the dense Wi-Fi zone targeted at the eye level. Thirdly, and most likely, raising any leg sidewise, left or right, makes the body tilt towards the opposite side. Therefore, the arm movement on that opposite side is likely to be confused with a leg movement on that side, especially if the TXRX pair is close enough to the body. However, we could achieve 80.65% accuracy at best with this dataset. Finally, we had 5 volunteers performing exercises using 4 equipment: total gym, curl bar, weight bench, and hand weights. There were 3 pairs of TXRX around these 4 equipments in a room. In the heat maps, we can see that link A achieves the most remarkable accuracy across the volunteers for a total gym and weight bench equipments, while link C achieves the highest accuracy across volunteers for hand weights and curl bar equipment. Here, the middle link B achieves slight improvements for some of the volunteer equipment pairs, but there is no consistent behavior where it achieves greater accuracy than the other TXRX links. As such, while link B does not itself achieve a greatest accuracy, it can still help to improve the overall system. Moreover, hand weight-based exercises are seen as the most confusing one for all volunteers. It can be due to the small movements of the hand weights compared to the activities performed at the other equipment locations. Next, we consider how well our system can predict which volunteer is doing which exercise as 2 separate problems. The top 3 bar charts show the accuracy of the multi-class classifier predicting the 4 different equipment stations using CSA captured with each TXRX link, where the least average accuracy is 93.39% using the link A. This demonstrates that even though only specific equipment is placed in the line of sight of each TXRX link, the models can still successfully distinguish which equipment is being used from any given link. Thus, we can see that link positioning is unimportant for equipment identification. Alternatively, the bottom 3 bar charts show that no single TXRX link achieves high prediction accuracy for person identification at all equipment locations. This is because person identification relies on understanding details such as height, weight, and the way in which a volunteer performs each activity. As such, we find that the highest achieved accuracy for each TXRX link corresponds directly to the equipment most closely located in the line of sight of the TX and RX. This is because equipment located in the non-line of sight may have environmental noise, such as fans, as well as the physical movements being performed, which may overshadow the human identifying traits that could more easily be seen in the line of sight. Overall, the greatest accuracy that we can achieve for hand weight is 85.6%, while all other equipment achieves greater than 91.1% respectively. To summarize, we can enlist our achievements in this study as to orchestrate a low-cost, device-free, and highly accurate physical sensing system, which is also capable of working with multiple volunteers and multiple TXRX links. As for our future scopes, we are planning to collect data with more volunteers, to develop an environment independent model, and to evaluate our system WiPT for tracking physical therapy patients over longer periods of time. Thank you for taking the time to listen to our work. If you have any questions, please feel free to email me or any of the others. Thank you, everyone.